Hello and welcome to the course on CS 301 Systems 4. Today we shall be talking about the overview of concurrency control. The computer industry is undergoing, if not another revolution, certainly a vigorous shaking up. The major chip manufacturers have, for the time being at least, given up trying to make processors run faster. Moore's law has not been repealed. Each year, more and more transistors fit into the same space, but their clock speed cannot be increased without overheating. Instead, manufacturers are turning to multi-core architectures in which multiple processors or cores communicate directly through shared hardware caches. Multiprocessor chips make computing more effective by exploiting parallelism, harnessing multiple processors to work on a single task. The spread of multiprocessor architectures will have a pervasive effect on how we develop software. Until recently, advances in technology meant advances in clock speed, so software would effectively speed up by itself over time. Now, however, this free ride is over. Advances in technology will mean increased parallelism and not increased clock speed, and exploiting such parallelism is one of the outstanding challenges of modern computer science. As far as the Moore's law go, what is Moore's law? Moore's law refers to Moore's perception that the number of transistors on a microchip doubles every 2 years, though the cost of computers is halved. Moore's law states that we can expect the speed and capability of our computers to increase every couple of years and we will pay less for them. Another tenet of Moore's law asserts that this growth is exponential. In 1965, Gordon Moore, co-founder of Intel, postulated that the number of transistors that can be packed into a given unit of space will double every 2 years. Today, however, the doubling of installed transistors on silicon chips occurs at a pace faster than every 2 years. Gordon Moore did not call this observation Moore's law, nor did he set out to create a law. Moore made that statement based on noticing emerging trends in chip manufacturing at Intel. Eventually, Moore's insight became a prediction, which in turn became the golden rule known as Moore's law. Moore's law implies that computers, machines that run on computers and computing power all became smaller, faster and cheaper with time, as transistors on integrated circuits became more efficient. Moore's law is the observation that the number of transistors in a dense integrated circuit doubles about every 2 years. From 2003 onwards, the clock speed flattened and could not be increased, and so the transistor size started reducing. Clearly, transistor counts still follow the exponential growth line. For example, AMD's EPIC processors with 19 billion transistors contribute the highest publicly disclosed transistor counts in processors to date. For comparison, NVIDIA's GP100 Pascal GPU consists of 15 billion transistors, so these numbers are consistent. With the upcoming introduction of 10 nanomillion process nodes, it is reasonable to assume that we will stay on the exponential growth curve for transistor counts for the next few years. These additional transistors will provide more cores. Thus, if you want to benefit from future processors over what you have now, make sure to have parallel workloads. So this is Moore's law in practice. Smaller size of the transistor and the increased clock speed heated the processor, and obviously this will lead to fire, and so you need to provide more cores. This is a uniprocessor, a single processor system where the clock speed was stable and it was obviously outdated. The processor with a shared memory. Now the processor and shared memory was mounted separately. The caches and the memory mounted on the same chip led to more concurrency. So this is a multi-core processor where everything is mounted on a single chip. So this is just an example of a multi-core processor. Now talking back to the history of concurrency, we have a single core machine with a single processor, a dual core machine with a dual processor, quad core processor where we have processors 1, 2, 3 and 4. If you compare the single core processor with the multi-core processor, you can see that you have in a single core, you have a single core, a single memory unit, whereas in a multi-core processor, you have two cores, each with an individual memory unit, and then they are connected via a bus interface to a shared memory. So looking at the traditional scaling up, as the speed increased, starting from a uniprocessor system where we start with a single processor system. So the manufacturer started making the size of the processors huge or bigger in size than the previous one. And we saw that the clock speed was increased, but still we had only a single process running on these cores. So the ideal scaling process was, it was unfortunately not so simple, but the speed up, we tried to achieve the speed up, but the number of cores started to increase. So we fortunately came to something which is called as a multi-core system where we have two cores. So each user core would be running on a single processor. So here we have four cores, four processors, and we have four user codes running independently on each core. Similarly, we talk about the quad core processor where we have four user codes running on different processors. So the actual scaling process, the worker threads have to be synchronized. So for example, if you want to paint a 4-room apartment with you and you have your 4 friends with you, so is easy than calling thousands of them to paint. So if you want to paint your apartment and you have only 4 of your friends to do this task, this will turn into a mess if there are no synchronization and coordination there. So between you and your 4 friends, there has to be synchronization and coordination. So if there is no synchronization and coordination, the entire task of painting the 4-room apartment will be messed up. So you need an efficient way to synchronize the multi-cores. Parallelization and synchronization require great care. So if you look at the figure here, you see that if there are only two processors and you have certain number of tasks being executed, it becomes easy if the number of processors are less. But as the number of processors go on increasing, the thread synchronization or the process synchronization has to be dealt with extreme care. So with this we come to the Amdahl's law, and the Amdahl's law says that bad synchronization ruins everything. So you can understand from the figure itself, if there is no synchronization, everything is going to mess up. So Amdahl's law says that how the different threads interact with each other. So this is basically, you can just consider a program where multiple threads operate on a buffer. Some threads only read from the buffer and other threads only write to the buffer. Any number of readers can simultaneously operate on the buffer. While a writer is operating on the buffer, no other writer or reader can be active on the buffer. Assume a pool of n threads where each reader and writer is a thread. Hereby, 90% of the threads are readers and 10% of the threads are writers. Each reader thread takes 2 seconds to execute and each writer thread takes 3 seconds to execute. The program terminates when the thread in the thread pool terminates. Now the task is, according to the Amdahl's law, what is an upper bound for the speed up of the above implementation on a 4-core processor. So you need to find an answer for this after I explain the 2 slides on Amdahl's law. Now the Amdahl's law says that the speed up can be calculated as it is 1 thread execution time upon n thread execution time. So the speed up can be written as P upon 1 minus P, which is a sequential fraction, or you can assume that this portion of the program can be executed in a sequential manner, plus P upon N is the parallel fraction or the concurrent fraction, where N is the number of threads and P is the fraction of work that can be parallelized. So consider an example where you have a 10-core machine and you have an application which is 60% concurrent and 40% sequential. So how close to a 10-fold speed up will be required? So you have to decide how much percent of your program is going to run concurrently and how much percent of your program will run in a sequential manner. Now, if it is a 60-40 combination, 60 of concurrent and 40 of sequential, the speed up will be equal to 0.6 upon 1 minus 0.6 plus 0.6 upon 10, which gives the speed up to be 2.17. So, your speed up is going to increase only by 2.17. If you make the program 80% concurrent and 20% sequential, the speed up comes up out to be 3.57. If you go on increasing the concurrent part of the program, or rather if the concurrency of the program has been increased to 90% and 10% sequential, the speed up comes to be 5.26. But what is expected on a 10-core machine for that application to run 10 to speed up 10 folds? We are not achieving the 10-fold speed up. So let's try out with 99% concurrent program and 1% of sequential. So if we calculate the speed up in this case, it comes out to be 9.17. So this is 9-fold speed up that we can achieve when you make 99% of your program as concurrent and 1% as sequential. So the question is, which paths are hard to make concurrent but still have a big influence on the speed up? So we define the term concurrency. So the dictionary definition of concurrency is simultaneous occurrence. A concurrent program is one defining actions that may be performed simultaneously. So a concurrent program consists of processes and shared objects. A process is a sequential program executed on some processor. The shared objects are built using shared memory or a computer communication network. Concurrent programs are often found in reactive systems. Systems whose outputs may affect their environment and therefore may influence subsequent inputs. Thus, a reactive system can control ongoing activities. A transformational system whose output is, by definition, unaffected by its input. A transformational system implements a function from input to output, and its correctness is defined in terms of its initial state and final states. So correctness of a reactive system concerns initial, final as well as intermediate states. Operating systems are the oldest examples of concurrent programs. An operating system manages execution of user tasks and controls processors and I/O devices that run in parallel. It has a natural specification as a concurrent program with a separate process controlling each user task and each hardware resource. So concurrent programs are useful wherever an application involves real or apparent parallelism in database systems, networks, industrial automations, and so on. Even when there is no real or apparent parallelism, structuring a system as a collection of processes and shared objects has proved effective for organizing large, complex systems. So in Python, Things that are occurring simultaneously are called by different names such as thread, task, processes, but at a high level, they are all referred to a sequence of instructions that run in order. So in the previous video, we also talked about what is sequential, what is concurrent, and what is parallel processing using certain examples. So these are certain examples which will help you to distinguish between what is a concurrent process and what is a parallel process. We also talked about various threads being executing at the same time where they have overlapping time periods. So concurrency, where overlapping time periods is which which has overlapping time periods, is basically a concurrent task. So it's basically a property of a system which enables overlapping of process lifetimes. So concurrency deals with multiple things at once, and parallelism talks about doing multiple things at once. We also need to understand the difference between the terms program, process, and thread. So a program is a code that is stored on the computer and is intended to fulfill a certain task. There are many types of programs, including programs that help computer to function and are part of the operating system, and other programs that fulfill a particular job. These task-specific programs are also known as applications and can include programs such as word processing, web browsing, or emailing a message to another computer. Programs are typically stored on disk or in non-volatile memory in a form that can be executed by your computer. Process. A process is what we call a program that has been loaded into memory along with all the resources it needs to operate. Thread. A thread is a unit of execution within a process. A process can have anywhere from just one thread to many threads. The terms multiprogramming, multiprocessing, multitasking, and multithreading. Multiprogramming, a computer running more than one program at a time, like running Excel and Firefox simultaneously. Multiprocessing, a computer using more than one CPU at a time is multiprocessing. So here we talk about multiple cores. Multitasking, task sharing a common resource like one CPU. So this could be termed as concurrency. This can be termed as concurrency. Multithreading is an extension of multitasking. Let's talk about concurrent program, parallel program, and distributed program. A concurrent program defines actions that may be performed simultaneously. A parallel program is a concurrent program that is designed for execution on parallel hardware. And a distributed program is a parallel program designed for execution on a network of autonomous processors that do not share main memory. Thus, concurrent program is a generic term used to describe any program involving actual or potential parallel behavior. Parallel and distributed programs are subclasses of concurrent program that are designed for execution in specific parallel processing environments. Where it is known that a single processor will be used to execute a program expressed in a concurrent form, the concurrency involved is sometimes referred to as pseudo-parallelism. A quasi-parallel program is a pseudo-parallel program in which processors execute cooperatively by transferring control to each other using a coroutine mechanism. Thank you for this video, and we shall continue for the next topic in the next video. Thank you.